First, we consider calculation of delta S for reversible phase changes. Phase changes can take place reversibly when they occur at specific conditions of temperature and pressure. For example, boiling of water liquid and condensation of water vapor at 100 degrees C and 1 bar are reversible processes. These conditions are shown by the orange dot on the phase diagram of water. Note that the boiling temperature of a substance depends on the pressure and that boiling and condensation are reversible processes for all states located on the orange curve, which we call the vapor-liquid coexistence curve or vapor-liquid phase boundary. Similarly, crystallization of water liquid and melting of ice at 0 degrees C and 1 bar are reversible processes. These conditions are shown by the green dot on the phase diagram of water. Note that the melting temperature of ice also depends on the pressure, and that crystallization and melting are reversible processes for all states defined by the green curve, which we call the liquid-solid coexistence curve or the liquid-solid phase boundary. Similarly, sublimation and vapor deposition occur reversibly for all states located on the black curve. Since vaporization occurs reversibly at constant temperature, we can write delta S equals Q reversible divided by T vaporization. Since vaporization occurs at constant pressure, the reversible heat of vaporization, Q vaporization, is equal to the change in enthalpy for the vaporization process. We saw in chapter 1 that this quantity was equal to the product of the number of moles N by delta vaporization H standard, the standard vaporization enthalpy change. So the change in entropy of vaporization for N moles of a substance is equal to N times delta H vaporization standard divided by T vaporization. Make sure you remember to express temperature in degree Kelvin, as we always should do in thermodynamics. Let us apply this equation for the boiling of 2 moles of water liquid, for which the standard vaporization enthalpy is equal to 40.7 kilojoules per mole. We convert the boiling temperature from degrees Celsius to Kelvin to obtain T vaporization equals 373.15 Kelvin, which leads to delta vaporization S equals 2.00 mole times 40.7 kilojoules per mole divided by 373.15 Kelvin, equal 218 joules per Kelvin. Let us now discuss the entropy changes for the surroundings and for the universe. The entropy change for the surroundings is equal to minus the heat for the phase change divided by the temperature at which the phase change takes place. So the entropy change for the surrounding is equal to minus the entropy change for the system, and the entropy change for the universe is equal to 0, as expected for reversible processes. Note also that the sign of delta S for a phase change is the same as the sign of the corresponding delta H. So, for endothermic phase changes, such as sublimation, melting, and vaporization, the corresponding delta S are positive, indicative that the phase change results in an increase in entropy or disorder for the substance of interest.